In Chapter 4, we want to take a look at solving second-order linear ODEs. In particular, we need to recall the standard form for a second-order linear ODE that has the form a2 of x y double prime plus a1 of x y prime of x plus a0 of x times y of x equals f of x, where the leading coefficient function is not 0. Well, let's call this equation 1. There's a simpler form of equation 1 if all of the coefficients end up being constant. And if we think of a2, a1, and a0 as being constants, maybe call them a, b, and c, and we leave f of x, the function, on the right-hand side alone, then this is a simpler version of this. And it's even simpler if the f function is identically the 0 function. In other words, we have a homogeneous equation. And if we have that form, then this becomes ay double prime plus by prime plus cy equals 0. Let's call this equation star. And even though it's a mouthful, the descriptor for this is that this is a second-order, linear, homogeneous equation with constant coefficients. This is going to be our prototypical second-order equation in contrast to the first-order equations that we were solving in Chapter 2. The theory here is completely different, and the solution techniques are completely different, so it's very important that you recognize when you have a second-order equation instead of a first-order equation. To motivate where these second-order problems come from, let's look at the standard spring mass system. So if we think of, we have a mass on the end of a spring that's attached to a platform. You could think of a tennis ball on the end of a slinky that's attached either holding to your hand or to a board or something like this. Then if we want to look at the physics that are involved in the motion of the spring mass system, we can think of when the mass just hangs there, it has some default equilibrium position. If we look at the displacement of that mass from its equilibrium position, and we call that position function y of 2, where we take the downward direction to be positive, then if y of t is the position or the displacement of the mass from its equilibrium position, if m is the value of the mass, if k is the spring stiffness constant, if b is the damping constant or the frictional constant that's due to the friction when this system moves through whatever the surrounding medium is, whether it be air or some kind of fluid. And then if we also look at the position of the platform, because it's possible to move this as well, if we think of that as a function of time and we call that f of t, then we have the position of the platform. Okay, now modeling the motion of the mass, we'll just use a very simple model. There are more complicated ones, but this is a plausible model. The forces that are present are, we have the force that's due to the spring, the restorative force due to the spring. If you stretch the spring, it wants to snap back. If you compress the spring, it wants to expand. And Hooke's law says that the restorative force of the spring is proportional to, but in the opposite direction of, the displacement. Secondly, we have a damping. A reasonable model for damping is that the force due to damping is proportional to, but in the opposite direction of the velocity, which would be y prime of t. And finally, the external force due to moving the platform, we could just call this f of t. Balancing the forces, we get that the sum of the forces is capital F, so that's the force due to the spring plus the force due to the damping plus the external force. Well, force is mass times acceleration. The force due to the spring by Hooke's law was minus k times y. The force due to the damping, we just took it to be proportional to, but in the opposite direction of the velocity, so we get minus b times y prime. And then the external force, we had that as f of t. Rewriting the mass times acceleration is mass times y double prime of t, and leaving everything else alone, we see that a differential equation is born in the unknown function y of t. And now if we throw all those terms that involve y to the left-hand side in an effort to make it match the standard form of 1, or equation star, we have an my double prime plus a by prime plus a ky equals f. This f here is called our forcing function, and you can see why because it's how we force the platform that might induce motion out of the mass. So this f is typically called the forcing function. If we look at a really simple beginning example where we're not moving the platform, then our f of t would be 0. This is called an unforced system. And when we do that, this equation here in black becomes, in red, my double prime plus by prime plus ky equals 0. And notice this is a version of equation star. Equation star was our second order linear homogeneous constant coefficient differential equation. So this is, you could think of this as just a math problem, but I wanted to root and ground this in some physical application so that you can see where these might come from. So this is just a prototypical problem that is a second order linear homogeneous constant coefficient differential equation. This is the differential equation for the unforced spring mass system. Okay? Now starting in section 4.2, our goal here is to find the general solution to differential equations that have that form. Ay double prime plus by prime plus cy equals 0, where the leading coefficient is not 0. We have to keep saying that because if the leading coefficient were 0, this wouldn't really be a second order equation because this term would vanish. Okay, we'll call that equation star like we did above. And so now if we want to try to solve these, let's just do what was done historically. Let's think what kind of function could possibly satisfy this differential equation. So if you think about what we need out of our function, we need that when we take our function, we take its first derivative, we take its second derivative, we multiply each of them by constants, and we add them together, that they'll all combine to give me a 0. So what that means is that the function, the first derivative, and the second derivative must all be like terms, because when we multiply them by constants, they all combine to give me a 0. So if you think of something like an x squared or an x cubed or a sine x or something like that, it's not likely that those functions are going to be the types of functions that this happens to. Definitely not for things like x squared and x cubed and the square root of x. We can talk about sine x a little bit later. But exponential functions are very natural because when you take the derivative of an exponential function, you again get an exponential function. And if I take the derivative of an exponential function, I'll get an exponential function. So the people that came before us said, why don't we look for a solution of the form e to the rt for some yet to be determined real number r. So t here is our variable, r is just a number that we don't know yet. And so if this is really going to be a solution, think back what we did in chapter 1, or in chapter 1 in the first few sections in chapter 1. We said if this function is going to be a solution, then when we plug this back in, we must get a true statement. So in preparation to do so, let's calculate y prime and y double prime. Y prime here by the chain rule would be e to the rt times r. Y double prime would be e to the rt, would be r times the derivative of r e to the rt, which would be r squared e to the rt. We know that if this is a solution and we plug all of these in, we must get a true statement. So I'll just substitute in e to the rt where I see a y, an r e to the rt where I see a y prime, and an r squared e to the rt where I see a y double prime. Now I know that if this is a solution, this equation must be true. So I'll just chip away at this. Notice I can factor out an e to the rt. What I'm left with is ar squared plus br plus c, and that whole thing has to equal 0. If these two things multiply to give me 0, either this is 0 or this is 0. Well, e to the rt equaling 0, that has no real solutions. So it must be that ar squared plus br plus c equals 0. This is known in our textbook as the auxiliary equation or the characteristic equation for the differential equation star. And notice this is just a standard quadratic equation. By the quadratic formula, we know how to solve for r. And so notice that the roots of the characteristic equation here determine the value of r. So if we just, the roots of this equation determine the values of r, and this is just a standard quadratic equation. And so once we know the values of r, then we'll have our solutions that are of the form y equals e to the rt. Now if you think back to basic algebra theory, that there's really 3 situations that you can encounter here. There's 3 different types of solutions or solution sets you can get for this quadratic, and they depend on the signature of the discriminant of the quadratic, and the discriminant of the quadratic is b squared minus 4ac. It's the part that sits underneath the square root in the quadratic formula. And so let's look at 3 cases. Case 1, suppose that the discriminant is positive. If the discriminant is positive, then if you just look back up here, this will give us 2 distinct real roots, r1 and r2. That means we're going to get a solution, what we'll call it y1, that goes with e to the r1t, and we get a second solution, we'll call it y2, that goes with e to the r2t. Moreover, if you take and form a new function, y of t, that's just an arbitrary constant c1 times y1 of t plus c2 times y2 of t, this is also a solution for any constant c1 and c2. So let's just make sure that you're tracking with me here. We found the roots r1 and r2 in case 1. We got two distinct real roots, r1 and r2. They gave us two solutions, e to the r1t and e to the r2t. So if we know r1 and r2, we know e to the r1t and we know e to the r2t. So we have two bona fide solutions to our second order differential equation. But the theory says that if we take any linear combination of these two, that will again be a solution, no matter what the linear combination is. So no matter what the values of C1 and C2 are. Let me show you why that's true. So take the differential equation ay double prime plus by prime plus c, and let's just, if this really is a solution, then what must be true is when we plug this back in for y, and we take its first derivative and its second derivative, and we calculate this, if this really is a solution, this has to come out to be 0. Because our differential equation was ay double prime plus by prime plus cy equals 0. So let's watch that happen. Let's literally substitute in this wherever we see a y. So I'll put it here with a first derivative, and here with a second derivative. So now when we go to take the second derivative of this quantity, we're just taking the second derivative of this. By our linearity property of derivatives, I just apply the second derivative to the function part, y1 and y2. I leave the constants alone. When I do this, I'm going to get an a c1 y double prime plus an a c2 y2 double prime. That's these two terms. When I play the same game here, I'm going to get a b c y1 prime plus a b c2 y2 prime. And here, there's no derivative to take. You just get c times c1 y1 plus c times c2 y2. Now, if you stare at that, we want to group this in a very particular way. So if we group the terms in them that have, we group the single underlined terms together. Notice these are all the terms that have y1s in them. We group the double underlined terms together. These are all the terms that have a y2 in them. If we separate them, the single underlined terms all have a common factor of c1, so we'll factor that out. And then what the rest of this has is an ay1 double prime plus a by1 prime plus a cy1. That's what we have here. And then the double underlined terms, they have a common factor of c2, so we factor that out. And what then we're left with is ay2 double prime plus by2 prime plus cy2. Well, now keep in mind, y1 and y2 were not random functions. y1 was guaranteed by our process above to be a solution to our differential equation star. So when we plug y1 into our differential equation, it must give us a 0. When we plug y2 into our differential equation, since it was a solution, it must give us a 0. So that means we get a c1 times 0 plus a c2 times 0. That comes out to be a 0. And just as we predicted, when we plug this, regardless of the value of c1 and c2, when we plug this into our differential equation, we end up getting a 0. That says that this linear combination of y1 and y2 is, in fact, a legitimate solution to the differential equation, regardless of the values of c1 and c2. Okay? Let's look at a concrete example so that we can get used to using case 1 of our characteristic equation above. So suppose we have the second order differential equation, y double prime plus 5y prime plus 6y equals 0. Notice it matches our standard form that we have. It's a second order linear, homogeneous, constant coefficients. So we want to write down the characteristic equation. Keep in mind our book calls this auxiliary equation. Both terms are in common usage. If you look at various books or various sources, I call it the characteristic equation. So our characteristic equation, remember, is AR squared plus BR plus C equals 0. Our A is 1, our B is 5, our C is 6. We need to find the roots of that characteristic equation, and you can do this any way you want to. Factoring will be the easiest way, but if you're not able to factor it, then using the quadratic formula is totally fine. Here I picked an example that factors really nicely. This factors into r plus 3 times r plus 2. So then our roots are when r plus 3 equals 0 or r plus 2 equals 0. So r equals minus 3 or r equals minus 2. Notice this is case 1 where we have two distinct real roots, two different real roots. So it tells us that one solution is e to the minus 3t, another solution is e to the minus 2t. Because remember, we were looking for solutions of the form e to the rt. We just happen to find two different values of r, so we get this 2-for-1 special where we get two solutions when we were just seeking any solution. But more than that, from what we just argued up here, we actually know even more. Not only is this a solution, not only is this a solution, but when we form the linear combination c1y1 plus c2y2, which is c1e to the minus 3t plus c2e to the minus 2t, that this will also be a solution. And notice how things have changed from our previous work. When we were dealing with a first-order differential equation, we got a one-parameter family of solutions as the general solution. But now we're dealing with a second-order differential equation, and notice how we naturally came about getting two solutions, and we actually get a two-parameter family of solutions. This is very, very important. This second-order equation should have a two-parameter family of solutions, and it does. Moreover, we haven't proven this yet, but this is in fact a general solution, which means every solution can be written in this form. Okay? So that leads me right here to this next question, and that is, does y equal c1y1 plus c2y2 encompass all possible solutions? In other words, when we write this down, is this a general solution? The answer is yes, but we need to qualify that. And in order to do that, we need a little bit of machinery. So that leads us to this definition. We say that two functions f and g are linearly independent on an interval I if, when you take a linear combination c1f plus c2g and you get 0, the only way that can happen is if c1 is 0 and c2 is 0. Think of it as the f function and the g function are so different that the only way they can combine to give you a 0 is in this sort of trivial way where we take c1 to be 0 and c2 to be 0. In other words, f and g are linearly independent on an interval if f is linearly independent if f is not a scalar multiple of g. Okay? So the only way that they're so different, the only way that you can combine and get 0 is if c1 and c2 are 0. If these two functions are not linearly independent, then we say that they're linearly dependent on an interval. Okay, and we're going to see in just a minute about why this notion of linear independence and linear dependence really matters so much. Let's look at a basic example. Suppose we take f of t as t squared and g of t as t cubed on the interval from minus infinity to infinity. These two functions are linearly independent because if we tried to form the linear combination c1t squared plus c2t cubed and we wanted that linear combination to equal 0, stare at that for a moment. The only possible way that you can make that happen for all values of t on the interval from minus infinity to infinity is if you pick c1 and c2 both to be 0. In other words, these functions are so different that the only way you can have them cancel each other out is if you sort of trivially do it with the coefficients both being 0. Okay. On the other hand, take a look at the example where f of t is e to the t and g of t is e to the t plus 1, again on the interval from minus infinity to infinity. Notice these functions are not linearly independent, they're actually linearly dependent, because if you form c1f plus c2g and you set that equal to 0, stare at that for a moment. You can pick values of c1 and c2 that'll make this combine to give me a 0. For example, if I pick my c2 to be 1 and I pick my c1 to be negative e, then this would give me a c1, so this would be a minus e times t, so this would be a minus e to the t plus 1, and then my c2 is just 1, so that would give me an e to the t plus 1. I get a minus e to the t plus 1 plus an e to the t plus 1, that combines to give me a 0. So notice, I was able to choose a constant c1 and c2 not both 0, such that this came out to be 0. Let's look at one more example. If we look at the functions f of t equals sine 2t and g of t equals sine t cosine t, again on the interval from minus infinity to infinity, in the homework you're going to see things like this. Are these functions linearly independent or linearly dependent? Well, if you just form the linear combination c1 sine 2t plus c2 sine t cosine t, so c1f plus c2g, and I want that to be 0, does that force c1 and c2 both to be 0? That's a question. Well, this isn't so easy to tell when you just eyeball it like this. But if you happen to remember the trig identity that sine of 2t is the same as 2 sine t cosine t, I now see that these two functions are scalar multiples of one another. If they're scalar multiples of one another, then they're copies of one another, and I will be able to pick a c1 and a c2 such that this combines to give me 0. So for example, if I just simplify this, I get this, and you can see here, for example, if I pick c1 to be 1, I pick c2 to be minus 2, these will combine to give me a 0 without picking both of the constants to be 0. I think this just tells us that we have to be careful. The definition is a little slippery. There's nothing wrong with the definition. It's just not foolproof to be able to tell when two functions are linearly independent when you just go from the definition. Something like this could easily get past us, and we think that these are linearly independent when they're not. So the idea here is we need a more systematic approach to determine linear independence or linear dependence. Ask and you shall receive. So here, the test for linear independence goes as follows. Let f of t and g of t be solutions of our differential equation on an interval I. Then f and g are linearly independent on our interval I if the Wronskian determinant, also known as the Wronskian, so the Wronskian of f and g, which is a function of t, this is defined to be the determinant of this little 2 by 2 matrix where you put f, g in the first row, f prime, g prime in the second row. And remember how you take the determinant of a 2 by 2 matrix from Cal 2 or Cal 3. It's just upper left times lower right minus upper right times lower left. So the determinant of this 2 by 2 matrix is f times g prime minus g times f prime. And our test for linear independence is if we have two solutions here, they're linearly independent if you compute their Wronskian and it's not 0. So the Wronskian not being 0 means your functions are linearly independent. So to summarize here, if the Wronskian in f of g is not 0 on the interval, then f and g are linearly independent, and it turns out that this is actually an if and only if. The Wronskian of f and g being 0 forces f and g to be linearly dependent. So you can think of the Wronskian or the Wronskian determinant as a foolproof litmus test. You can just calculate it, and either you get 0 or you don't get 0. If the Wronskian is 0, then the functions are linearly independent. If the Wronskian is non-zero, then the functions are linearly independent. Let's take a look at an example. Let's just go back to the same example that we did above. Suppose that we're in case 1 of the characteristic equation. Our y1 is e to the r1t. Our y2 is e to the r2t. Let's suppose that we're in case 1 where r1 and r2 are real and they're distinct. So let's suppose that. Let's calculate the Wronskian of this y1 and this y2. So that's the determinant of my y1, my y2, my y1 prime, my y2 prime. Then I calculate that determinant. So it's e to the r1t times r2 e to the r2t minus e to the r2t times r1 e to the r1t. Let's simplify that. So if you notice here, both terms have a common factor of e to the r1t, e to the r2t, e to the r1t, e to the r2t. So let's factor that out. When we do, we're left with an r2 minus an r1. And the question is, if we look at this, can this equal 0? Because if this can equal 0, then that means the Wronskian is 0, which means the functions must be linearly dependent. But stare at this. If this is going to equal 0, and that's a question mark, then either this is 0, or this is 0, or this is 0. Well, this can't be 0. E to the r1t doesn't have any real solutions. Equals 0 doesn't have any solutions. E to the r2t equals 0 doesn't have any real solutions. And then if r2 minus r1 is going to equal 0, then it must be that r2 equals r1, but we said that we're in case 1. So R1 and R2 are distinct. So that has no solutions. So it tells you that it's impossible for this to equal 0. That means the Wronskian of our y1 and y2 above is impossible to be 0. So that means y1 and y2 are linearly independent. This is very powerful. Notice it says no matter what numbers you get for R1 and R2, if they really came from case 1 of our characteristic equation analysis, then the Wronskian every single time must be non-zero. So it means these creatures every single time are two linearly independent solutions. And the reason that's so important is a key component of our theory is the following. If y1 and y2 are any two linearly independent solutions, not just solutions, they have to be linearly independent of our differential equation star, then when you form a linear combination of the y1 and the y2, any linear combination of them, that's guaranteed to be a general solution of star. And what we mean by a general solution is every solution in the universe of the differential equation where these, in this situation, can be written in this form. So you're guaranteed that you haven't missed any solutions if you build this as your overall solution. So what that says is that in case 1, when we have y is c1 y1 plus c2 y2, that is c1 e to the r1t and c2 e to the r2t, then that is a general solution of star. Very, very important. We have one solution, we have another solution, we take a linear combination of them to get the overall general solution for that case. Okay, so what happens if we're in a different case? So we already covered case 1 where the discriminant was positive. What happens if the discriminant is 0? So if we have a b squared minus 4ac, that was our discriminant, is equal to 0. Then if you remember from your basic algebra theory, if you scroll back up here and we look at our quadratic right here, if we look at our solutions to our characteristic equation, they look like this. If the discriminant is 0, then this is 0. So we get exactly one real root. It's minus b over 2a. And so we got one root. It's a double root, remember. And so if we look at that, what does that tell us for case 2 in terms of generating our solutions? Well, we know you get, when your discriminant is equal to 0, you know you get one repeated real root. We'll call it r. We know its value is minus b over 2a. And then that tells us that one solution is e to the rt for that r. But remember, we need a second linearly independent solution in order to build the general solution. And we can't just merely use this again because these would not be linearly independent. In order to build a general solution, we have to get a second linearly independent solution. So we've got one. Where do we conjure up the second linearly independent solution from? And so that's the question. How do we get a second linearly independent solution? And so here I'm just going to sort of pull a mathematical rabbit out of the hat. And in a few sections, I'm going to show you where this came from. But for right now, I'm just going to declare it to you. The way you build the second linearly independent solution in the case 2 scenario is you just take your first solution, e to the rt, and you multiply it by t. And you might say, where did that come from? I totally admit that I just pulled that rabbit out of a hat here. We don't know where this came from, but we can still check that it's true. If you check and you put this back into the differential equation for case 2, you will see that it is actually a solution. And more than that, you can check that this solution is linearly independent from this solution in case 2. Because you can just calculate the Wronskian of y1 and y2. That would be the determinant of y1, y2, y1 prime, y2 prime. If you calculate that determinant, this is what you get. When the algebraic and calculus dust settles, these terms cancel each other out. You get an e to the e to the 2rt, and e to the 2rt is never equal to 0 for any real r. So that tells us our Wronskian of these two is non-zero, therefore this is linearly independent from this. Now I didn't show this, but you do need to check that this is a solution. It is. If you plug it back into the differential equation, it will check out. This part is just proving the linear independence. Once again, this is very, very powerful because it says that our conclusion is that in case 2, when the discriminant is 0, you get one repeated real root r. One solution is going to be e to the rt. A second solution is going to be t e to the rt. These are guaranteed to be linearly independent solutions. And therefore, from our previous big theorem, when we form any linear combination of these two linearly independent solutions, this is guaranteed to be a general solution for our differential equation in case 2. All right, let's look at a concrete example. A concrete example is if we look at y double prime plus 6y prime plus 9y equals 0. In this case, our a is 1, our b is 6, our c is 9. This does meet our standard form for a second order linear homogeneous constant coefficient equation. So we should use the characteristic equation. Our characteristic equation is ar squared plus br plus c equals 0. This factors very nicely into r plus 3 quantity squared equals 0. And so we get one root. It's a double root, or root of multiplicity 2. We get r equals minus 3 as a double root. Because it's a double root, we know we're in case 2. So that means one solution is going to be e to the minus rt, in other words, e to the minus 3t. Our second linearly independent solution is going to be t e to the minus 3t. And then our general solution is going to be a linear combination of these two. So c1 e to the minus 3t plus c2 t e to the minus 3t. Once again, it's very important that this is a 2-parameter family. These c's must be different. You have to have 2 degrees of freedom here in order to capture the general solution. Okay, so we've covered case 1 and case 2 of the characteristic equation scenario. Case 3 is going to be covered in the next section, so we're going to punt for that for now. But what happens if you had initial conditions? I do want to touch on, suppose you had a differential equation, second order linear homogeneous with constant coefficients, so you're going to use a characteristic equation, and suppose you had initial conditions. It turns out that for a second order differential equation, you're going to need 2 initial conditions, so 2 pieces of information specified at the same t-value. Normally you're given you're given y at 0 and y prime at 0, but they could be given at another value of t. So they're just values for y and y prime specified at the same t-value. It doesn't have to be 0, but it commonly is. So you could think of this in terms of physics. If y is position, then this would be initial position. This would be initial velocity. Okay, so let's look at an example. Suppose you had y double prime minus y equals 0, along with the initial condition, y of 0 is 1, and y prime of 0 is 0. Okay, so we're going to use our characteristic equation. Our a is 1, our b is 0, our c is minus 1. So our characteristic equation is just ar squared plus br plus c equals 0. So this is r squared minus 1 equals 0. Our roots are then r equals plus or minus 1. Since these are distinct real roots, we're in case 1. So we know our general solution. Our 2 solutions look like e to the 1t and e to the minus 1t. Our general solution would look like c1 e to the 1t plus c2 e to the minus 1t. This is our general solution. This is exactly what we did before. Nothing is new. Here's where the new little layer of newness comes from. When you have your 2 initial conditions specified, now you have 2 pieces of information, and you need 2 pieces of information to nail down these 2 constants. So when I go to apply the first initial condition, I'm just going to take my general solution. I'm going to evaluate this at t equals 0. That's going to give me a c1 e to the 0 plus a c2 e to the minus 0. All of that has to equal 1 because my initial condition at 0 was 1. Notice this gives me c1 plus c2 equals 1. So that's 1 equation and 2 unknowns. So just hold on. To apply the second initial condition, I first need to take the derivative of y. So looking at this, I'll take the derivative of y. I'll evaluate that derivative at 0. When I do, I get a second equation in those 2 unknowns. So notice this gave me, it's a little bit different than what we did in the first order case. So it's a little bit more involved. This ended up giving me one equation and two unknowns. This gave me another equation and two unknowns. When I take these two equations and two unknowns together, we solve them by our favorite method. And when we solve them, that will give us the values of C1 and C2. You can solve these any way you want to. Here I just use the elimination method. I get that C1 is a half. I get that C2 is a half. And then what I should do, just like we did in chapter 2, I should return to my general solution, and I should plug back in the values that I found for my constant. It just so happens in this example that they're the same number. They're usually not, but I'm going to get a 1/2 for C1. I'm going to get a 1/2 for C2, and then this would be the solution to the initial value problem. It's still following the same motif of you find your general solution, and then you use your initial conditions to nail down the constants that are involved. Okay, so this covers case 1 and case 2 of the characteristic equation. Like I said, case 3 is covered in the next section, but you should get some practice calculating Wronskians, calculating two different solutions, making sure that they're linearly independent, and forming the general solution in the case 1 and case 2 situations of the characteristic equation.